Okay, this is chapter 8, number 28. But before I forget, for those of you who are not at school on Friday, also added on to the homework was to see the video chapter 9, number 22. So, chapter 9, number 22 is about impulse. This one, however, is about a skier who's on top of a sphere of some sort, and he starts off just sitting there. He's not moving yet. And he's actually directly on top, or she is directly on top. So we have the force of gravity, and we have the normal force. The question is, at what point does she lose contact with the sphere? At what angle? When she does lose contact, let's draw the forces on her. So we have her mass is still there, but now she's lost contact with, just as she loses contact with the sphere, the normal force disappears. So the normal force equals 0. Alright, so really the only force on her is the force of gravity. So, the first thing to do, by the way, this was a problem on one of the AP exams, except instead of having it be a skier, it was a marble that was rolling off another sphere. And what we're doing is actually simpler than the one on the AP exam, because with a rolling marble you need to take into account moment of inertia and all this stuff that we haven't quite learned yet. But this works for what we're trying to do. Okay, so the first thing to do, oh yeah, and this was a free response question. It was not a multiple choice, so this would be way too hard for a multiple choice. Find the sum of the forces. Now, in terms of we're looking at part 2, because that's really the question is what's the angle at, and so that happens at part 2. Well, the sum of the forces is kind of strange because we can split the force of gravity to 2 parts. There's my straight dashed line. And here's the angle. Okay. So you could say that it's here's the y-axis and here's the x-axis. Okay. So some of the forces towards the center, because remember, usually we do it in the x and in the y direction, but here we have an acceleration that's towards the center, and anything that twirls around in a circle has an acceleration towards the center. So, excuse me. And so we have this line is the center, is the force that's towards the center. That's mg cosine theta. No more normal force. That is at the critical point when she loses contact, the normal force goes to 0. So it's 0. So equals not ma. Well, you can do ma towards the center, but the acceleration to the center has the formula v squared over r, the radius. So that's how you do that. You replace a with v squared over r whenever it's circular or moving in a circular motion. It's not ma, it's mv squared over r. Okay. Let's look at the sum of the forces in the other direction, because we only took account of this component. There's also this component. Well, that would be in the x direction. So sum of the forces tangent to the circle would be mg sine theta. Here it's a different acceleration. It's not an acceleration towards the center, it's the tangential acceleration. So now we have two formulas. Both of them have theta. We know the mass. The mass is m. I put it up here at m equals m, r equals r, because it could be that our answer is in terms of m and r. We know d, so we know m. We don't know v, however. We know r. We don't know acceleration, the tangential acceleration. So we've got two unknowns and two formulas. However, it's not the same unknowns. That's a problem. We need to find another formula that at least has the same unknowns. Could be either theta and velocity, or the theta and tangential acceleration. More after this.